Hey everybody, Rich Stroffolino here with Gestalt IT, and want to take some time to talk to you about a little bit of a trend I've been seeing in the chip industry and where I think we're going to be going in the near future. We've been firmly in the age of general purpose computing for well over 40 years. The age has been virtually synonymous with the dominance, if not all-out monopoly, of the x86 architecture, and by that, let's face it, we mean mostly Intel. Now, it's no secret to say that x86 is in a little bit more of a precarious position today than it was even as short as a decade ago. It's never been able to compete with ARM on mobile, and now we're starting to see ARM creep into form factors beyond just simply phones and tablets. While the dream of ARM in the data center mostly still remains a dream, it's a lot closer to feasibility than it was just a short time ago. But in the last few years, we're starting to see another phenomenon emerge that could be even more disruptive to Intel: the importance of semi-custom silicon. This approach has been used with great success on game consoles for a long time. The chip maker, whether it's AMD or IBM or even Motorola back in the day, provides a basic silicon platform that doesn't need to be created from the ground up. The device manufacturer can specify customizable modules to enable a desired functionality. In gaming, this means that modern consoles are largely based around AMD APUs, but with a lot more beefed up graphics, physics processing, and the like. This isn't to say that Intel doesn't do any custom silicon work, but their approach is generally focused more on binning CPUs to meet the frequency and processor requirements of large clients. Think of your typical hyperscaler. This lets companies specify a particular processor specification outside of the commercially available Intel stock. So if semi-custom silicon is so great, why hasn't it eaten the world yet? Well, it has to thread a pretty particular needle. To justify the additional design and production costs, the benefit has to be significant over commodity solutions, which typically, thanks to Moore's law, have increased in efficiency and power over the years. If your workload is hyper-specific, it's all for better investment to just create a fully custom ASIC or FPGA and call it a day. But again, that's when Moore's law was delivering significantly increased performance year over year. You could really just throw some x86 at it and call it a day. Need a server? Throw some x86 at it. High-performance switch? Throw some x86 at it. Storage array? Throw some x86 at it. Game consoles could flourish with this approach because they could assume economies of scale and had graphical needs that were just one of the few things that commodity x86 couldn't produce on die, basically requiring separate cards. This left an opening for AMD and that APU design. But if you haven't noticed, Moore's law isn't quite what it used to be. While CPU designs are certainly still advancing, getting more performance or better performance per watt is coming at slower and slower intervals. This means you often can't design a system or device and know that the performance you need will be there on a general purpose platform in a year or two. Now, add in the increasing prevalence of workloads that we'll call, let's say, general purpose resistant, things like artificial intelligence and machine learning. Due to their inherent parallelizations, GPUs were able to offer a lot more efficiency than traditional general purpose compute. But NVIDIA and others quickly came to see that this general purpose GPU approach was approaching its limits. From their highest-end Volta to more consumer-focused RTX cards, NVIDIA is now creating specialized cores to meet the needs of certain workloads. You have traditional graphics cores, of course, but tensor workloads for AI and ML, and ray tracing cores as well. The age of the unified do-everything CUDA core is coming to an end. Recently, we've seen this extended even further. Microsoft's recent hardware event got a lot of press for the announcement that the company was getting back into the phone market. Spoiler, never bet on Microsoft in the phone market. Now you know. But a little buried in that big news was the company had worked with both AMD and Qualcomm to create device-specific hardware for current generation devices. The AMD announcement was a little less interesting. Their Ryzen Surface Edition processor, basically just adding a little more graphics grunt, one more graphics core on there, and power management to let it fit into a slimmer design. This is very similar to what Intel's already been doing with their Xeon Scalable processors, just on a more consumer level and trumpeted and marketed a lot more specifically. But Qualcomm, on the other hand, built a specialized ARM processor for Microsoft, the SQ1. This is a customized version of Qualcomm's Snapdragon 8CX platform. It's unclear what all the customizations are, but definitely includes a custom thermal profile, integrated AI accelerator, and pushes frequency on some of the cores. And this is from Microsoft, a company that, while unfathomably enormous in a lot of ways, is really not that big of a device maker in terms of volume. I suspect that this was developed to eventually go into other partner OEM devices, with Microsoft getting a temporary exclusive and probably paying a pretty penny to do so. But if that plays out, it still means that Microsoft is making custom silicon for Windows. Apple pioneered this approach with ARM on iOS, but it's a remarkable step for Microsoft to take. Now we're seeing ARM opening up the potential floodgates for semi-custom silicon. They'll soon support custom instructions, letting SoC makers add unique application-specific instructions to Cortex-M CPUs without risking overall software fragmentation. This will have major implications for IoT and embedded use cases. Just think about cars, for instance. And again, points to the limits of general-purpose computing. Although it's notable that ARM is being very, very careful to say that this will not fragment software. Just want to make that very clear. This approach will also allow for easier integration for coprocessors, essentially an admission that a general-purpose Cortex core isn't applicable in all instances. Now, I'm not saying that general-purpose computing will go away or even become a minority of use cases, but with the slowing performance gains of ubiquitous x86, getting performance improvements will increasingly depend on a semi-custom approach. Hey, thanks for watching, really appreciate it. If you enjoyed it, give it a like and subscribe to Gestalt IT to get all sorts of video content. We do podcasts every other Tuesday, and we're hoping to do videos like this every single Friday. If you want to get more of our content, head over to gestaltit.com and follow us on Twitter at GestaltIT. You can also follow me, Rich Stroffolino, at Mr. Anthropology. That's MR Anthropology on Twitter. And until next time we meet, remember everybody, have a super sparkly day.